Okay, so this lecture is about the probability theory and mathematical statistics. I'm pretty sure all of you have a bit of knowledge or understanding of at least basic probability theories and mathematical statistics. So this part would be basically a review of what you already know, but later, either later this lecture or next lecture, we will extend our knowledge to beyond what probably you already know. Let's start with the simple one. It's a univariate discrete random variable. So suppose this x is a random variable. Okay, so x is a random variable, especially discrete random variable. A discrete random variable means that the random variable x can take finite number of realizations. So the set of possible values or realizations of x is the jargon for this set is called the support of x. In my notes, I use this abbreviation as SUPP of x. It's discrete, so you can write this way: x1. Let's use superscript: x1, x2, x3, x4, and so on, up to a finite number. But the support set can be infinite. So this is finite, but it may be infinite. So x1, x2, x3. So it doesn't really matter whether the realized possible values of x is finite or infinite, so long as the values are discrete. We call this random variable a discrete univariate random variable. When you have discrete random variable, you can assign probabilities for each value. So for example, you can think of, let's use the finite case. So you can assign the probability that your random variable realizes value x1, probability that your random variable realizes x2, and so on. So this maps the support set to probabilities, right? So this is a function. There is a function we call probability mass function, which probability mass function, or PMF, is a function from the support set set to a value between 0 and 1 probability. Okay, and of course here I'm using f to denote the probability mass function, and I also am going to use subscript x to indicate that this function is also associated with the random variable x. So you may have two univariate random variables like x and y, and suppose the support of x is 1, 2, 3, and the support of y is 1, 10, 100, 1000. And you may use f sub x to denote the PMF of x, and f sub y to denote PMF of y. The probability mass function has to satisfy the axioms of probabilities, which is this: the fx of s, fy of s as well has to be greater than or equal to 0, and especially fx of s is greater than 0 for any s in the support of x. In fact, the support set is defined by the set of values whose PMF is greater than 0 in the discrete case, and the summation of fx of s for all possible s has to be 1. That's the that's one of the axioms of probabilities. And what else? If fx of s is 0, then s is not in the support set in a discrete case. Okay. And in the discrete case, fx of s means probability that your x, here this is your x, takes value s. So the PMF has a meaning, it's probability. Okay, you can also think about the cumulative probability. So cumulative probability distribution function CDF as an abbreviation. Quite often we omit the cumulative, so we may use probability distribution function, and even shorter distribution function df. Often we use the uppercase letter, so fx or fx s is associated with fxs, and the relation between CDF and PMF is this. CDF is summation r less than s or equal to s fxr. So you're going to sum the PMF up to this point s. Okay. Okay. In mathematical statistics, we use expectations. For expectations, this is an operation. We use this operator E solve a random variable x. Okay, and the definition of this is summation for all possible value of s, and s f x of s, that's what expectation is. More general function, so the expectation of a function of random variable also exists. So expected value or expectation of g of x is summation s g of s f x s. So expectation means this operation, summation some function multiplied by its PMF. That's what expectation is. For some expectations have names. So for example, this expectation is called the mean of the random variable x. This means therefore mean of random variable g of x. And this expectation, expected value of x minus e of x squared, has a name. This is called the variance of x. And we are going to use v of x or var of x. Then variance of gx is g of x minus expected value of g of x squared. That's gonna be the variance of g of x, right? Okay. And this is what? Summation s g of s minus expected value of g of x squared f x of x, not x, s, right? Okay. Let me do an exercise, an example. Suppose your variable y, let's say w, is this. W is described by the following PMF. F of w minus 1 is 1 over 3. F of w 0 is 1 over 3. F of w 1 is 1 over 3. Then the expected value of w is 0, and expected value of w squared is minus 1 squared times 1/2 plus 0 squared times 1/3 plus 1 squared times 1/3, which is 2 over 3. Okay. You can compute the variance of W. You can compute the variance of W squared. Okay. All right. Now let's do the bivariate discrete random variable. A bivariate discrete random variable is a vector, two-dimensional vector of random variables. So let's say x a bivariate random variable x consists of x1 and x2. Okay, this is a bivariate. Now naturally you can think of a trivariate random variable, say w. W can be w1, w2, w3. It's gonna be a trivariate. Okay. Now let's get back to the bivariate case. And how would you define the PDF of bivariate random variable? Okay. So first of all, the support. Now let's just erase this one. So we are going to focus on the bivariate case. Support of x is set of vectors, right? x1, x2, 1, 1, x1, x2, 2, 2, x1, x2, 3, 3, and so on. If it's finite, then you have x1, x2, m. It can be infinite as well. Let's just focus on finite bivariate random variable. A bivariate random variable with finite support. You may call this a vector x superscript 1, this x superscript 2, x superscript 3, x superscript m. Then we can define the PMF in the same way. Probability that your x is x1, which actually means probability that x1, x2 is x1, 1, x2, 1. But more familiar exposition is probability that x1 is x1, 1 and x2 is x2, 1. Okay, that's the PMF. The PMF of bivariate random variable is called a joint PMF. Okay. What about joint PDF? joint CDF, then the associated CDF can be written. It can be written as uppercase letter x1, and that's gonna be probability that your x is less than or equal to x1, like in the univariate case. But what you have to be careful here is this less than or equal to, is in a vector sense. What do I mean by vector sense? It means this. It means probability that x1, x2 is less than or equal to x11, x21. And this vector inequality means that element-wise inequality. So this means probability that x1 less than or equal to x11, and let's just omit n because we will mean by comma the end x2 less than or equal to x21. That's what this CDF means. Okay, so this is a joint CDF. Okay. If you sum up according to one axis or one coordinate, you get the CDF, the PMF, sorry, this one. So if you sum up this function, the PM function, with respect to one coordinate, in this case x2, so x2 with respect to all possible x2, this operation gives you f x1 x11. So this is the probability that your x1 variable takes value x11. Okay, since it's this probability is called the marginal probability. So this is marginal PMF. Similarly, you can sum up with respect to x1 of the joint x, x1, x21. It gives you f x2 this has to be subscript, right? x1 f x2 at x21. So this is another marginal PMF. Okay. The marginal CDF, for example, f x1 s is summation x summation r less than s f x1 r, that's what this function is. And since the marginal PMF is defined by this operation from the joint PMF, you get this summation r less than s summation x2 f x, the joint, and r comma x2. Right. Here the next concept is that we want to talk about is the conditional probability. Actually, this is the one of the most important concepts for regression. So conditional probability is this. Conditional. Let's talk about conditional PMF. Conditional PMF, we use this notation f, the low-case letter function, x2 given x1. It means that conditioning upon x1 being certain value. This notation means probability that x2 is s given x1 is t. This is the concept conditional PMF. And to compute the conditional PMF, we use the Bayesian rule. Is this f x t comma s. That's probability that your x1 is t, x2 is s, and divide this by the marginal of the conditioning variable f x1 at t. That's the conditional PMF. Conditional PMF is like just a new random variable. You can define, you can think of the conditional PMF, conditional random variable is like a new random variable. So you can define the PMF, conditional PMF, you can define conditional CDF. Conditional CDF this way, f x 2 given x1, s given t is summation r less than s f x 2 given x1 r given t. Okay, so just like the relation between CDF and PMF of a univariate case, you can just sum up the PMF to obtain the conditional PMF to obtain conditional CDF. Okay, this is probability that your x2 less than s given x1 equals t. And what you have to be careful is this is not probability that x2 less than s given x1 less than t. Okay. Okay. You can extend this joint marginal conditional probabilities to a multivariate, not just bivariate but multivariate, like trivariate, four variable, something like that, random variables. So for example, let's think about a trivariate random variable W, which has three element random variables, W1, W2, W3. Then f of w at vector w1, 1, w2, 1, w3, 1 is probability that w1 is w1, 1, w2 is w2, 1, w3 is w3, 1. That's what the PMF is. What about marginals? So you can think of the following marginals. F of W, W1, 1, W2, 1, and S, summation S. This is one marginal. This is another marginal. W1, 1, S, W2, W3, 1. And there's another marginal as well, SFW, S, W21, W31. And this will give you probability that W1 is W1, 1 and W2 is W2, 1, which we may use F W1, W2, W1, 1, W2, 1. In a similar manner and similar definition, we may define this marginal. We may use this notation for this marginal, W1, W3, and W1, 1, and W3, 1. For this one, we have F of W2, W3 at W2, 1, W3, 1. What you can see here is joint distributions can be also marginal distributions. Here in this example, this function, all these three are joint PMF of bivariate random variables, but they are marginal PMF from the trivariate random variables. Okay, this is also marginal, summation S, summation R, F W, W1, 1, R, S, which is probability that W1 is W1, 1, which you may call F of W1 at W1, 1. Summation S, summation R, F W, R, W2, 1, S is a marginal too. In a similar fashion, you may call FW2 at W2, 1. Summation S, summation R, FW, R, S, W3, 1 is also a marginal, which you may call W3, W3, 1. Okay, all of them are marginal, and these three are joint as well as marginal. Okay, what about the conditionals? So you can think of this conditional, F W1 given W2, W3 at W11 given let's say S and T. Okay, it means probability that W1 is W11 given W2 is S and W3 is T. And like before, this conditional can be written in terms of joint F W W11 S and T, and divide this by the marginal of conditioning random variables. Our conditioning random variable is a bivariate random variable W2 and W3. So we have F W2 W3 evaluated at S and T. Okay, that's one conditional. Another conditional is F W1 W2 given W3 at W1 1 W2 2 given S. This is probability that W1 is W11 and W2 is W22 given W3 is S, which is FW W11 W22 S over FW3 S. Okay. So if you have multivariate, then you can do a lot of different operations. Now let's talk about the moment. Moment of a multivariate random variable is a vector of moment of each coordinate. So this is going to be expected value of x1 and expected value of x2, which is summation s f x1 s summation s f x2 s. Right, that's what it is. What about a trivariate random variable? Expected value of w is expected value of w1, expected value of w2, expected value of w3, a vector, which is summation s f w1 s summation s f w2 s summation s f w3 s. Okay, what about the variance, the second order moment? Oh, by the way, yeah, what about this? Now consider a function g of x, which is g of x1 and x2, which is simply x1 plus x2. Okay, in this case, expected value of g of x is this expect summation s summation r s plus r times f x s comma r. Okay, what if your transformation g is vector valued? For example, suppose your g of x is g1 x1 x2 and g2 x1 x2, and it's like this: x1 plus x2, here x1 times x2. Okay, then expected value of g of x is expected value of g1 x1 x2, expected value of g2 x1 x2, which is summation double summation SR G1 R S F X I comma S summation SR G2 R comma S Fx R comma S. In this case, G1 R comma S is R plus S, and G2 R comma S is R times S. Okay. Now let's consider the second order moment, the variance. When x was a univariate case, the variance was this. The variance of x was expected value of x minus expected value of x squared. In a multivariate case, the variance of x is expected value of x minus expected value of x. It's a column vector. Remember, we are going to use column vector as a default vector form, and multiply this by x minus e of x prime. When x is a bivariate case, expected value, and this is what? This is x1, x2 minus e of x1 minus e of x2 multiplied by x1 minus e of x1, x2 minus e of x2 prime, which is expected value of x1 minus e of x1 squared, x1 minus e of x1, x2 minus e of x2, and x2 minus e of x2 multiplied by x1 minus e of x1, and then x2 minus e of x2 squared, right? And this matrix e of x1 minus e of x1 squared, e of x1 minus e of x1, x2 minus e of x2, and the same here, and expected value of x2 minus e of x2 squared, right? And this one is called this, as well as this, is called the covariance between x1 and x2. And how you compute the covariance is this: summation R S s minus e of x1 multiplied by r minus e of x2 fx sr. That's what this expectation is about. What about expectation of conditional random variables? Expectation of x1 given x2 is t. Then you may regard what happens. You may regard this whole thing as a new random variable, okay, which has PDF f x1 x2 at s given t. Okay, so the expectation therefore is summation s times f x1 given x2 s given t. That's what this expectation is. What about the variance of x1 given x2 is t? And that's this summation s. It's expected value of x1 given x2 is t, this new random variable, minus expected value of x1 given x2 is t squared, right? That's what this is. But notation wise, we don't like this strange notation here because it's confusing. So instead we use this notation. x1 minus expected value of x1 given x2 is t squared given x2 is t. Okay, and how you compute? Is summation s minus e of x1 given x2 is t squared f x1 s, sorry, x1 given x2 s given t. Okay, that's the variance, the conditional variance. From today on, oh, okay, that's it. That's it for now. So in page 25, I have discussed about the concept of dependence, linear dependence, orthogonality, and so on, degeneracy. Oh, here, this variance matrix this matrix is called the variance matrix or covariance matrix or variance covariance matrix, whichever you like. I often call this a variance matrix. When x1 and x2 are independent, statistically independent, then the covariance is 0. So the variance matrix is a diagonal matrix. Okay. If x1 and x2 are not necessarily independent, but they are not the same random variable or a deterministic transformation of one another, then this variance matrix is a positive definite matrix. If one random variable here, in this case x1, we have two random variables, x1 and x2. If x1 random variable is a deterministic transformation of the other, more specifically, it's a deterministic linear transformation or affine transformation of the other, then the variance matrix is not positive definite, it's positive semi-definite. Statistical independence. Statistical independence is defined by the PMFs. So let's get back to the bivariate case here. So in this example, the element variables x1 and x2 here, x1 and x2, they are statistically independent of each other if the joint PMF is a product of marginal PMF for every possible realization. So if this is fx1 x11 times fx2 x21 for all possible x1 and x2 realizations, then the random variable x1 and x2 are independent, statistically independent. Okay. All right. I guess that's it for now. I'm gonna continue with the continuous random variables next lecture.